Good afternoon, everyone.
Okay.
It's my great pleasure to introduce Praveen Palanisamy, who is currently a senior AI engineer in the autonomous systems group at Microsoft. He works on developing platforms and solutions for autonomous systems. Prior to that, Praveen was a researcher at General Motors R&D, where he developed perception, planning, and decision-making algorithms and architectures for autonomous driving. His inventions in the autonomous systems space has led to more than 15 patents. He has authored a hands-on book for developing intelligent agents with an aim for providing an easy-to-follow guide for the readers to understand and implement software agents that learn to solve tasks. Praveen obtained his master's degree in robotics from Robotics Institute from Carnegie Mellon University and holds a bachelor's degree from VIT, India. Thank you so much, Praveen. The floor is yours.
Thank you for the introduction, Adi. And thank you all for coming on this Friday afternoon. And so today I'll be talking more on the work we've been doing on the multi-agent deep reinforcement learning for connected autonomous driving. So this was work that I have been working on when I was a researcher at General Motors, and then I've been working on this space for a while. So this is the agenda for today, today's talk. And first, I'll just start with introduction to set the context for the domain that I'll be discussing today, and then I'll go on to the MACAD-Gym, our multi-agent connected autonomous driving platform, the research platform that I'll be discussing in detail today, and then also the exciting autonomous systems work that we do at Microsoft. And yes, so let's get started. First, I will start with an overview of what autonomous driving is, and then connected autonomous driving, and then what is it when we say we are using reinforcement learning, and start with a brief overview of the fields, and then I'll jump right into the platform. So first, Holly gave a very good introduction about me, so I'll just skim through it. I'll actually skip through it. And yes, so currently I'm a senior AI engineer at Microsoft, and previously I was a researcher. And so to set the context for the domain of today's talk, I'll just say what it means when we say which space are we dealing with. So first is the autonomous navigation space when it comes to where it's being applied. And so autonomous navigation includes having a map of the environment, be it indoor, outdoor, 3D or 2D, and then locomoting in that environment. So for example, driving is one form of locomotion where we have a vehicle and then it's on a road, and then we would like to find our path and drive towards our destination from A to B. And that's the specific space that we will be talking today about with respect to the application side of things. And there are other navigation, like in aerial navigation, autonomous aerial navigation, and indoor robot navigation in other spaces. But today we'll be focusing more on the autonomous driving space. And on the other side of the spectrum, where we're starting with the whole field of artificial intelligence, and we'll narrow it down to the machine learning space that we'll be focusing on. And under that, as you all know, there are three main subdivisions. One is supervised learning, where you have train models using data with labeled data, where, for example, humans label the data saying what the algorithm is seeing or hearing when it comes to speech or text or images. And with that labeled data, we are training some massive function approximation models, for example, in deep learning using supervised learning. And that has seen a lot of success, as you all know. And on the other spectrum, we have the unsupervised learning, where we do not provide the algorithm with labeled data, but we expect the algorithm to learn from unlabeled data. And this can be for generative modeling or many other applications. And the other part of this machine learning space is the reinforcement learning, which is the focus of this talk, where there's no special labeled data set as such. It's more driven by interaction with the environment. And we'll go down into how that's set up and what forms the components of reinforcement learning a little bit later in the slides. And then deep reinforcement learning is a combination of, or I should say, applying deep learning methods um, to the reinforcement learning field, be it on the policy representation or modeling of the environment. It's about utilizing deep learning in the context of reinforcement learning, and that makes it deep reinforcement learning. So overall, we'll be talking about this space. And yes, so let's get started, and then let's start with what autonomous driving is. So autonomous driving usually is split into several components, or it's easy to focus when we try to address. So in the previous slide, I talked about how autonomous driving is focused on navigation, a subset of navigation in more or less 2D space, but it does involve, as you all know, perception, planning, and sensing and control in dimensional space. Even though the car is driving on the road, it needs to be aware of the environment in the whole 3D space. So that sets the context of why it needs such advanced sensing modalities. So we'll start from the left and then we'll progressively go towards the right. So starting with the sensing, so the autonomous cars you might have seen any of the versions being developed either by General Motors, Cruise Automation, or Waymo, Uber, or any other autonomous driving companies. So I might have seen all these cars with all these sensor suite. So they have cameras, multiple cameras, LiDARs, and GPS, radars, and many other sensors actually are on them. And that forms the basis of what enables the cars to drive autonomously. And all of these sensing modalities offer a holistic view of the environment. And this is 3D view of the environment, even though the car is tasked to be driving along the road. And even with the elevation profiles varying, we still consider the road to be more or less on the 2D plane, if you consider look at it that way. But then the problems involved are so complex. And so sensing modalities help us perceive these environment. And so under the perception, there's can be localization and mapping and other tasks as well, depending on how we decompose the system. So localization mainly is about, given all the sensor information that I have, how does the vehicle determine where in this world the car is and which particular side of the road, like lane of the road, and all of that determination. And localization mainly driven by GPS like sensors, but qualities and incorporated using sensor fusion to accurate localization to the lane level information. And then there's mapping, which involves, could be dynamic mapping on the fly, like the approaches taken by Tesla. And also could be statically mapped because we don't upgrade or change the road networks that often. So all the OEMs or other autonomous driving companies usually maintain a map database that is being stored and retrieved depending on where the autonomous vehicle is operating. So that forms part of the perception side of the things. And when it comes to planning, there are multiple components. It can be further subdivided, or actually even a separate component on its own is prediction of what the other vehicles or agents in the scene is doing, based on what we have sensed and what we have perceived. What do we predict to be the future forward action of the other agents. And planning for ourselves, it could be path planning on where do we want to go. This is the higher level path planning of, okay, I need to go from point A to point B, and which side of the lane should I be in? Am I taking the exit, or can I wait? So all these determination is what the autonomous vehicle does for itself. And so it could also be about behavior planning, where the vehicle decides, given all these from the passengers, for example, they want to reach from A to B in the minimum time, but at the same time, they want to make sure the jerk is minimized. So they don't want to feel a bumpy ride, but at the same time, they would prefer to reach the destination sooner. So the autonomous vehicle chooses its behaviors, whether it needs to be aggressive or whether it needs to be like slow, and all this determination can be done in behavior planning in addition to every more details. And also the trajectory planning on when is a good time to make a right lane change, when it's a good time to stay on course or follow the vehicle or overtake lane changes, and all this tactical planning for the actual trajectory. And then the control involves executing those trajectory using any controllers. And that's the overview of how the autonomous driving space is composed of. And when it comes to connected autonomous driving, what we have is an enhanced set of capabilities where all the vehicles are the road components, road actors, where it could be vehicles, it could be pedestrians, it could be motorcyclists, and even the signals, traffic lights. They're all connected in the sense they share information. For example, the traffic lights share their traffic signal phase and time, so through messages. And the vehicles can know what the phase is at the moment and how long it will take for the signal to transition to next phases, so that they can plan their routes and their drives more efficiently. And it leads to overall optimization of the overall travel. And so that also amounts to, as we are progressing towards the connected autonomy, so all of these connection through DSRC, which is a dedicated short-range communication channel between cars, vehicle to vehicles, or vehicle to infrastructure, like the traffic lights, or even it is vehicle to pedestrians and other modes of sensors. And there's also the more ubiquitous 5G network that is coming up, being developed. So that enables faster mode of information sharing and even higher levels of autonomous capability through even remote control operations and other. So this brings in a lot more feature as well as complexity, because you have a lot more data now to make use of and develop. So that's about the connected autonomous driving. And so this defines the space that we'll be focusing on. And with respect to what kind of algorithms and things we'll be using, so this is more on the reinforcement learning side, on setting the context on. So in the reinforcement learning setting, we have an agent and we have the environment. So this is a single agent reinforcement learning setting. So we have the agent, which observes a state, ST, and that's being kind of from the environment. So, and then the agent observes the state and takes an action, A, and that gets executed in the environment, and then the environment responds back with a reward. And this is the basic overall flow for reinforcement learning in very simple words. And the reward signal is the single signal that helps the agent get better in the task. And so in this setting, so we progress from a simple Markov process to a Markov reward process. And then finally in the RL, we make use of Markov decision process, sequential decision making. And that is governed by, it's been researched for several decades now. and provides a very good framework. But I would like to make a note here that in this single agent reinforcement learning setting, we have one agent, and every other component or every other actor, agent, or anything else is considered to be the environment, or at least part of the environment. So that is a distinction that is something that we'll revisit when we are in the multi-agent reinforcement learning setting. And now we can go into what is deep reinforcement learning. So in reinforcement learning, we have these components. The policy that the agent takes, which is a distribution over actions given state. And it could be deterministic policy or stochastic policy, depending on the environment and its policy. And then we have the value functions. So it could be the state value function, V, or action value functions, usually represented using Q. So these are the components that the agent makes use of or has algorithms to improve. And there's also the model. So in model, there are separate model-based reinforcement learning and model-free reinforcement learning. Most of the advancements in recent times that you have seen, be it in Atari games or other applications, have been on the model-free reinforcement learning, but there are also more promising methods with model-based reinforcement learning, where the environment representation, the model involves or includes the representation of the environment and the Markov MDP transition models, which is explicitly modeled when we do model-based reinforcement learning. And the model is also an estimate, not a true, because we do not have full access to the MDP. If the agent did, then it would be it is possible to obtain a deterministic policy through Bellman optimal equations that we could determine in an optimal policy if the MDP is known. But the whole problem is we do not. And in model-free reinforcement learning, we do not explicitly model the environment or the transition models, but in model-based, we do. And the other component is the memory, which is more or less not necessary per se, but then there are algorithms that make use of episodic memory or experience replay memory that helps in addressing some of the efficiency when it comes to reinforcement learning. So the sample complexity is usually high for these algorithms, and some of these episodic memory representation, especially with off policy learning, is something that helps us to train agents in a reasonable amount of wall clock time. So those are the building blocks. And now when we make use of deep learning in all of these or any of these components, that's when we kind of make it reinforcement or deep reinforcement learning, because we do not change the underlying principles or anything of reinforcement learning. And it's merely the representation of the policies or representation of the value functions or learning of the models or representation of the memory, for example, the neural network-based memory representations. So that usage of deep learning in the reinforcement learning context is what makes this field of deep reinforcement learning, which is the prominent success factor in recent times. So next, we'll finally get to the multi-agent deep reinforcement learning. And this is like a good and fun way of looking at what multi-agent reinforcement learning enables us. So I'll just quickly play this video from OpenAI, which kind of allows, or they have shown training of multiple agents, which allows training agents that learn a lot of behavioral factors that you might think are usually part of some human behavior factors. But in this stages, as you can see, the blue agents are more or less trying to hide from the red agent. And so they try to kind of form a sense of the environment and try to move around, blocking, and all of these learning on, okay, to avoid being found by the red agent, we need to make sure it doesn't have straight line of sight, and we need to figure out how to move these blocks around. We need to figure out the openings, and all of these are not something that we tell it, or the agents were told explicitly. All of these are driven by pure reward mechanism, and they cooperatively figure out that they need to work in collaboration, cooperation, to be able to figure out a way to achieve the objective for the blue agent, which is to hide, and for the red agent, it is to seek them. As you can see, there are lots of emerging behaviors that arise in such a vast setting of multi-agent reinforcement learning. So that's more or less the promise that the multi-agent setup offers, where all of these are trained from scratch, no prior knowledge of navigation, object detection, or hiding or seeking. So they figure out all of these strategies while operating in this multi-agent environment. So that concludes. I hope that gave a good overview of the components that, or the field that we will be focusing on for our presentation. Now I will dive into the platform, the research platform that is the main focus of this talk. So multi-agent connected autonomous driving. And so this platform is a research platform for developing policies for autonomous driving in the context of how do we represent the autonomous driving problem as a reinforcement learning first, and then how do we extend that to multi-agent reinforcement learning, because inherently the problem involves interaction with a lot of other agents. And so this is the top layer you see is the platform that we'll be discussing about today. And that's built on the simulation platform, which is called Carla. This is an open source project, has been in development since 2018. But so just to give an overview of what the platform enables, you can see modeling of different actors in the scene. And this is also realistic in the rendering sense, so that when we use camera-based algorithms for perception, you kind of get a good view into how it would actually translate when we actually deploy these algorithms on the real world. So this is using a game engine called Unreal Engine, but this is mainly geared towards providing a simulation platform so that we could kind of train these agents in a simulation environment because of the hard constraints on the real environments, where it's not like a game of Atari where we could train an agent by letting it simulate and then play, make mistakes, because this is real world. So this simulation engine enables us to simulate some of these scenarios that we're interested in. And the MACAD-Gym platform builds on top of the simulation engine to set up the platforms and the environments that we will need to begin or even research and develop methods. So next I will go into, okay, so I'll talk with the motivation first. So why do we need such a research platform when we can just make use of some kind of simulation, like the basic simulation capabilities and that? So it's, and then why do we need a multi-agent learning setup? It's all motivated by the fact that driving involves usually complex setup, and so interactions between other agents that is nearly impossible to be described exhaustively through rules or code. You can't really say, okay, this, when you come up to an intersection, the agent or the car would have to wait for other cars coming up to the intersection, and you would have to determine the right of way, and the car that came first makes its first move if it is a stops and control intersection, and things like that. So it's nearly impossible to exhaustively describe such things through code or rules. And also autonomous driving systems, mainly because of the intractable representation, for that reason, cannot be pre-programmed with exhaustive set of rules to cover all possible scenarios. And so deep RL provides that framework. And so the capability to learn and adapt to changes in the driving environment is crucial for developing autonomous driving systems. And that is, I think, the essential component to scale beyond geofence operation of design domains. So for example, we have autonomous cars that drive today in a fixed neighborhood or a fixed routes. And that is good for fixed shuttle routes and fixed domains of operation. But if we really want to scale it beyond that, we need to be able to train algorithms or agents that can actually adapt to changes in the environment. And so RL is promising to do that. And that's one of the reasons. But as we discussed before, the single agent formulation ignores interaction with the other agents. So that's the main motivation behind why this work involves multi-agent RL framework. And so with the capability that is needed to adapt, so the learning agents can potentially discover such complex interactions automatically through exploration, as we saw in the case of the hide and seek example from OpenAI. And so they can learn these complex interactions automatically. The automatic part is important because it is really not tractable for us to describe it manually as a set of rules or through code. So that's why we would need this automatic learning through exploration, and the agents can evolve their behaviors and actions to be more successful in their driving based on their experience gathered through interactions in the driving environment or a long period of time in simulation. So we can make use of this massive capabilities of simulation to train these agents and really scale it to cases that we wouldn't even imagine. And that's the only way of developing systems that actually operate without limitations. And so deep reinforcement learning provides that promising and scalable framework for developing such adaptive learning based solutions. But it is hard to apply RL algorithms to life systems, as we discussed before, especially to physical systems like robots and safety critical systems like autonomous cars. And moreover, RL-based learning is not very sample efficient. That's also something that we touched upon earlier. So we need really millions, actually billions of interactions with the environment. And that's really feasible only in the simulation world. But thankfully, that's something we can make use of. And that's why the platform that we are discussing today exists. And so one way to kind of overcome the limitations by using is the limitation was about how do we scale this, because we cannot run on the real world is through the simulation platform. And as we discussed, the single agent reinforcement learning, which makes use of the Markov decision process. The agent is there's one sole agent and every other thing is part of the environment. And so in Markov decision process, or sometimes even formulated as a POMDP or partially observable Markov decision process, the agent acts in a stationary environment to learn an optimal behavior policy. But however, to this point, driving involves that complex interaction between multiple intelligent, it can be artificial or human, agents in non-stationary environments. So that's why the main focus is on using multi-agent learning frameworks where the interaction between other agents are explicitly modeled. And that's what enables us to help train train agents that can utilize and learn those complex interaction mechanisms as well. And so connectivity among vehicles are becoming more and more available and ubiquitous. And this has been made viable through decades of research in dedicated short-range communications and other vehicular communication methods. And as we discussed before, 5G deployment, which is being increasing, and also it's penetrating to the autonomous vehicles domain. So that opens up the space where we can truly utilize the multi-agent setting, because there are, how do we model, so in multi-agent setting, there are communications happening and the agent needs to cooperate, or so all of these mechanisms would require some form of formal or informal communication channels. And these V2V, V2I, V2X are the channels that opens up this space. So with that, let's go look into how we could formulate the problem. So the interaction, so like I mentioned, the MDP setting in a single agent setting, the other agents are the interactions with the main agent or the main actor or the main agent for which we would like to develop the policy for, is the only actor or the agent, and the environment is modeled as part of that Markov decision process. And other agents are treated to be part of that environment, irrespective of the, the nature of the other agents or the types of other agents, and even the source of interactions. So that is not a good way of representation, the single agent Markov decision process representation, because it fails to account for the fact that there indeed exist other agents. It's not the only agent that's acting in that road, for example, while driving. So when the Markov decision process fails to account for the presence of other intelligent and adaptive agents in the environment, it leads to conditions that violate the stationarity and the Markov assumptions, which is the main assumption of the MDP um, framework. And in particular, when other intelligent agents are present in the environment that are capable of learning and adapting their policy. So for example, consider the case when there are two autonomous vehicles in the same scene, the other autonomous vehicle is also trying to learn and improve. And so if you consider this environment to be stationary, it is really not the case, because the other agent is also trying to learn and improve as our main agent is trying to. So to account for such multiple agents and multiple state configurations, we can take the Markov decision process and generalize it using the Markov games, which redefines the game theoretic stochastic game formulation in the RL context. So in several of the real world multi-agent problem domains, like the one that we're discussing today, which is the autonomous driving, assuming that each agent can observe the complete state of the environment without uncertainty is like unrealistic. And due to the limitations associated um, with the agent, actually the car in this case, which is, so for example, the concrete example why the agent cannot observe is because on the car, we have the sensors on the vehicle, but each sensor has its own limitation in terms of how much the field of view and how far and how intensive, for example, the radar or the LiDAR hit points come back. There are so many variations. It's never going to be the case that we can observe the environment fully. So that's why we need to take into account the partial observability in this context. And that's why we chose the partially observable stochastic games formulation. And that extends the stochastic games to problems with partial observability. And like In the same way, the Markov games was defined. We are redefining the partially observable stochastic games here in this context of RL as partially observable Markov games, and which is represented using the tuple ISAOTR, in which we will use I to represent the finite set of actors or the agents in the scene, which comprises the multi-agent system. And then S is the finite set of states. So we assume that the environment states is a fixed set, or it's a finite set, because every agent acting in that will also have an observation, which is a subset of this finite set. And A represents the set of giant actions, where A sub I is the set of actions available to agent I, because we are considering the multi-agent setting. Each agent has its own configuration, and one agent could be the autonomous car, the other agent could be an autonomous motorcycle, the other agent could be a traffic light. So all of these agents have a different set of actions. So we have a different action space. And so O is the set of giant observation, where O sub I is the observation set for agent I. So each agent has its own sensor configuration. Each agent has its different modalities in sensing. Some agents have real, like the traffic lights, or motorcycles have limited sense of sensor suite on them. So the observation space is also dependent on the agent nature. So that's different set for each agent. And the transition T representing the probability of transition from a given state S and given action A to the next state is the Markovian state transition. And where A is the set of actions in state S, and which one acted or applied in state S results in transition to the next state S dash, resulting in a giant observation O. And R sub I is the reward function for agent I, because each agent has its own objective and has its own reward mechanism. So that's the formulation that we will be using for this. And I should make a note that while the partially observable Markov games formulation for the autonomous driving problems enables us to approach the problem without making unrealistic assumptions, because we're not saying that every other agent is stationary, they don't change, or we're not saying that every other agent follows a fixed set of policy. And so we are relaxing all those constraints and really trying to address the problem in the realistic sense. But it does not enable computationally tractable methodologies to solve the problem, except under some simplified structure. And like, so special structures exist, like two-player zero-sum games, but details are in the paper that specifically addresses the structural simplification that we need to do in order to make this problem tractable in the autonomous driving space. So next we'll discuss about what the platform provides or enables one to do. So we kind of provide a first taxonomy in terms of the different kind of research problems that can be addressed, different types of tasks that can be solved under this platform. So MACAD-Gym provides OpenAI Gym compatible environments where you could study the various tasks. You can, depending on the nature of agents, it can be homogeneous, where all the actors or the agents in the scene are cars, or it can be heterogeneous, where it could be a mix of cars and motorcycles and others. And also depending on the nature of tasks. So it can be a cooperative task where you want to find the minimum time trajectory for all the agents in the scenario, so that all of the cars cooperatively reach a minimum time trajectory. to reach their destination, or it could be independent, where each car acts on its own with its own policies, or it can be sometimes competitive, or it can be a mixed strategy environment. And with respect to the nature of environment itself, it can be partially or fully observable, and then the scenario can be different on its own. It can be a highway driving scenario, it can be intersection driving scenario, and it can be several other scenarios. And it can also be adversarial if we set the goal for the environment to be, and it can be multi-agent or single agent. So the tasks and other classifications are provided just so we could expand this to apply to several situations that one may be interested in. So the task classification is actually sometimes important, that we can learn nearly global optimal policies, as we discussed, when if all the agents are cooperative. And it also helps agents that can learn to communicate and benefit from learning to cooperate, like one of the observation we made in the OpenAI hide and seek. So likewise, such environments help in the development of efficient fleet of vehicles, for example, that cooperate and communicate with each other to reduce the congestion and eliminate collisions and optimize traffic flows overall. So yes. And then there's also a unique scenario ID to represent the particular scenario if you want to benchmark your own agents, and then a version number for the environment. So next we'll look into, with that taxonomy in mind, so let's formally define what the goal of each agent is and how do we approach it. So the goal of each agent is to maximize the expected value of its long-term future reward given by the following objective function, j sub I. And so where pi sub minus I is the set of policies of agents other than the main agent I. And in contrast to the single agent setting, the objective function of the agent in this multi-agent setting depends on the policies of the other agents. So this is important, as we are taking into account that the other agents are also intelligent and they can change their policy. And so value-based multi-agent deep RL. So pi sub I, as I mentioned, is the policy of the other agents. And the value-based methods in the multi-agent setting is given by the equation here, so which follows from derivations that extends for the multi-agent setting. And so the optimal policy is the best response depending on the other agent's policies. So this pi I star, the star represents the optimal policy for agent I, and that, as you can see from this expansion, is dependent on the policies of other agents. Computing the optimal policy under this method requires the transition probability to be known, transition model of the environment to be known. So the state action value function definition can also be derived. It's in the appendix of the paper if you're interested. And so from this, we can also derive the policy gradient to imply policy gradient-based methods. So that's the setting, and we'll look at how this. So in one of the instantiation of how we could approach or train agents for this, so we have a decoupled actor learner architecture, wherein, so this is a distributed learning RL setup where we can have different agents represented using vehicle 1, vehicle 2, vehicle N, and they have their own actor policy and also their own local experience replay memory on the centralized learners setting on the left. So where the experience is local XP1 is the experience replay memory for each agent, and they can share that with the global learner. So the learner makes use of the experience gathered from all of these agents in an off-policy learning setting, where a centralized learner makes use of these different experiences to train policy, which can then be distributed. The policy parameters can be distributed to the local agents for more of an online update mechanism. And can be also decentralized learners, like on the right, where the learner actually is part of the vehicle or the agent and locally, and what is being shared or pooled is the experience memory. So both of these offer some advantages and disadvantages, and depending on how we would like to deploy, one can choose one or the other. And this is a product as part of the starter agent framework for this platform to build upon. And in the interest of time, I'll quickly go to the next slide showing a quick result wherein, as you can see on the left, so there's a car. The cars are randomized so that the policy learned is not fixed for a particular car type, actually. So this is in one particular environment where homo and com independent, actually, it's just an environment short form for homogeneous, non-communicating, independent, partially observable, intersection driving, a multi-agent scenario. So we saw the nomenclature or the taxonomy on how things are represented or named. And so the goal of the maroon colored car, if you focus on the picture here, that is static. So the maroon colored car is to traverse the intersection and make a right turn. And the goal for the cola van that you see on the right-hand side of the intersection is the goal is to make a right turn. And the goal of the white top car. So these cars are different than in the video because, as mentioned, that the car types are randomized, so that the policy is not very fixed on the dynamics of that particular vehicle. And so the cumulative mean and the max rewards are shown on the plot on the left bottom. And on the right-hand side shows a plot of how the three-agent system learns progressively over 9.2 million training steps. And the final snapshot of the agent's data at two snapshots, one at 1.1 million steps, and the second snapshot 4.6 million steps, where you can see they're like in a gridlock situation. So this is the picture on the middle where it shows all the agents are in a gridlock because there is full learning. And but yes, as they progress, you can see that finally they're able to kind of reach their maximum cumulative rewards. So yeah, if you're interested in this line of work, feel free to get in touch. And yeah, so here are some information. And there's also, the code is open source, and you can build on top of it, or you can utilize that for your own research works. And let's see. So next, I would like to go and give a quick overview of what we do as part of the autonomous systems at Microsoft. So let's get started. So are you able to see my screen still?
Yes, we can see it.
Okay. So I'll play a quick video. Maybe I'll not have time for the whole video to be played, but depending on your interest, I'll just provide the pointers. You can actually go over to learn more about what we do here, part of the Microsoft's autonomous systems team. So we tackle more problems than just driving or any specific industry. So I'll probably enable audio. But maybe probably you should so we work with different customers and different.
You need to share the sound for your computer as well if you want to show this video.
Okay, so that's with Zoom.
Yes, it's in the Zoom settings. You can share the sound of your computer as well.
Okay, I think it's probably not sharing this. Okay, so I'll provide the pointers to this video where you can actually look into and learn how we are supporting different industries, different use cases. Here you see an autonomous aerial vehicle that we help train for several applications. And okay, back to our slides. So yes, so we are actually hiring for autonomous systems, and this is one of the simulation platform we have, which is also an open source platform. This is for more if you're interested in aerial simulation and developing autonomous aerial systems. But yes, while the video loads, I'll just, okay, so here what you're seeing is how you could simulate aerial vehicles with a real-time depth view and segmentation view and also cameras. So this provides a full array of sensors that you would use on a aerial vehicle. And the environment is a sample environment, but you could utilize it to fly the drone in any environment and collect sensor data or do inspection or do simulation for package delivery or several such applications, as you can imagine. So I think we have about 6 minutes left. I'll take about a minute more and then we can take questions. Actually, yes, that concludes my presentation. So we can take questions while we are watching videos.
Okay, thank you so much, Praveen. It was a very interesting talk.